Okay then, good morning everyone. So we got two lectures from me this week, this morning and tomorrow afternoon. So what we're going to look today is there's one or two of the series convergence tests that we didn't mention yet up to now. Last time, remember, we looked at the comparison tests and the ratio test. The comparison tests allowed us to decide on the convergence status of a given series, meaning whether it converges or diverges. It allowed us to do that by comparing it with a series that we already know about. The series that we use for the ones that we already know the behavior of, the comparison ones, were the hyperharmonic series, which were these ones, the sum over every power of 1 over n, as n goes from 1 to infinity. This is called a hyperharmonic class of series. And for the one value p equals 1, this diverged. That was the harmonic series. But for any value of p greater than 1, this converged. So it gives us a whole class of convergent series that we could use to compare to other series. And if p was less than or equal to 1, this diverged. So we give a whole family of convergent series and divergent series. And these are ones that you can use to compare to other more complicated compound series. So generally, if the series that you're trying to test is some ratio of polynomials, if the term an of the one you're assessing, if it's a ratio of polynomials in the index variable here is n, then normally the approach to take is to compare it to one of these using the comparison test, either the standard comparison test or the limit comparison test. The way the standard comparison test worked, which we discussed last time, was you compare the term of your series to the known series through an inequality. And if you're comparing to a convergent series, you want to show that your term an is smaller than the convergent series. Because remember, infinite series of positive terms, they converge when the terms shrink very fast. The terms shrink to 0 fast enough. So if you can show an inequality like an is less than or equal to cm, if the cm is behaving well, in the sense of getting small fast enough so that the sum of all the cm's converge, and if that inequality holds, an less than cm, that means the an's are behaving better. They're getting smaller even faster, so the series, the sum of an, will also converge. And then a similar thing goes for when you're reaching a conclusion of divergence. If you show that an is greater than or equal to dn, the dn are the terms of a divergent series. Well, if it's diverging, that means the dn aren't behaving good enough. They're not converging to 0 fast enough. Okay? And so if our an's are greater than those dn's, then neither are the an's converging to 0 fast enough. So if the sum of the dn is divergent, then so will the sum of all the an's. That's what's known as the standard comparison test. Another variation on it is the limit comparison test, and this is often easier. This can often be more straightforward to carry out. And this time, the comparison you make is by figuring out what the limit of the ratio of terms is. Where you take the term you're testing, the term from the series you're testing, which would be this an, and you're dividing it by the comparison term, and you're working out the limit. Now, if you get a finite limit and you used a convergent term from a convergent series, then you'll know that R series, the sum of AM is convergent. And the reasoning here, the way to think about it is, if this limit comes out as a finite number, then it means in the long run, approximately, AM is approximately equal to L times CM. So that means the series we're testing in the long run is approximately a fixed multiple of this convergent series. So if the convergent series is going to get closer and closer to some finite limiting value, so will our series that we're looking at. Because its long-term behavior is approximately to act like a fixed multiple L of the convergent series. Similarly, if the term you're using, the comparison term, is a divergent term, then, and if the limit comes to a non-zero finite number, or indeed the limit doesn't exist at all, if it's infinity, if this is an unbounded increasing ratio, then the series we're looking at is divergent also. And the reasoning there is much the same. If this limit L exists, that means in the long run, our term AM is approximately this fixed multiple L of the dm term. So if the series, the sum of all the dm's, if that's divergent, that's exploding in value without any upper bound, then so will our series that we're examining, okay? Because it's acting like a fixed multiple of the divergent. Okay. So as I say, very often the comparison series that we're using, the series which is taking the place of CM or DM, that's going to be one of these hyperharmonic series. And we also looked last time at the ratio test. And the ratio test is where you're kind of comparing the series to itself, in the sense that you're looking at the limit of the ratio of consecutive terms from your series. If that comes out to be a fixed value, which is strictly less than 1, well, we base the conclusion on what the value of that limit is. Because if this limit exists, that means in the long run, our series is acting like a geometric series. Okay? Because each term, well, when you wait long enough until this approximation becomes very, very close, each term in our series is approximately L times the previous one. Okay? Because the ratio AM plus 1 over AM will be very close to L. If you multiply both sides by AM, you get that AM plus 1 is very close to L times AM. Now that's the behavior of a geometric series, or something which is very close to being geometric, each term being a fixed multiple of the previous term. And we've already completely analyzed and understood geometric series that are exactly geometric, where each term is an exact fixed multiple of the previous term. We know that they're convergent when the fixed common ratio, this fixed multiple L, we know they're convergent when that multiple has absolute value less than 1, and divergent when it's greater than or equal to 1. Well, now what that means for the ratio test is, if you get this limit out, and if this ratio does converge to this limit where it's strictly less than 1, then we know our series is convergent. If this limit is strictly greater than 1, then you know our series is divergent, because it will be acting approximately like a divergent geometric series. The problem is when this limit comes out at exactly 1, then we're not so sure. Okay, you can say our series is acting approximately like a geometric series where the fixed ratio is equal to 1 in the long term, but that's the borderline case between that case where the fixed ratio is 1. That's the borderline case between convergent behavior and divergent behavior in the geometric series. So because our series, we know it's only approximately acting like this borderline case, that's not enough information to know whether our series is going to be convergent or divergent. It still could go either way, because all we know is it's close to the border between convergent and divergent behavior. So it could be on either side. Okay. So that's a quick review of what we covered last time. So something we haven't covered yet, and I'll just say a few words about. There's two remaining tests. Two remaining tests, and this is the alternating series test and the root test. Okay. So just switch over to the overhead for this. So theorem 2.8 is the alternating series test. Now, what is an alternating series? An alternating series, this is one of the form. So you're adding up terms am, but there's a alternating sign in front of it. M here. Okay. Where let's say the AMs are all non-negative. If the AMs are all non-negative, then the terms of this series are alternately positive and negative. Okay? Because that -1 to the power m will be moving back and forth between the plus sign and the minus sign as m increases. Okay? If we also know that the AMs are decreasing, now there's a slight misprint in the notes here. You need to know that AM is okay. I've got this inequality is the wrong way around in the notes, so just need to correct it. It's in the wrong direction. In the notes, it says AM plus 1 is greater than AM, but if I'm talking about them decreasing, of course, AM plus 1 should be less than AM. So correct the direction in the notes. So then you have to think about what our partial sums of this series is doing. The partial sums, if the series is alternating, that means the partial sums are stepping up and stepping down. Okay? Because each time the new term you're adding on is either a plus sign or a minus sign, and that goes alternately. So your partial sums, at whatever intermediate value they have, the next value they have will step down a bit, and then they'll step up a bit, and then they'll step down a bit, and up a bit. Well, what this theorem says is if these step sizes are converging to 0, then this series will converge. Otherwise, it diverges. And there's a good picture that can help you kind of visualize what's going on there. So SK, remember, is the partial sum from n equals 1 to k minus 1 to the power m am. If we graph the partial sums, now what the first one, when m equals 1, that'll be a minus sign, so it'll be a minus sign. So I should start there. Okay. So 1, 2, 3, 4. The partial sums are going to fall into this kind of, some kind of pattern like this. This kind of behavior is going to continue. You see, the first partial sum will be a negative number because it will be minus a1, and I've said that all the terms am are positive. So the first partial sum s1, which is just equal to the first term of the series, that's going to be some negative number. Then you're going to take a positive step. Okay, because the next term will be -1 squared times a2, so it's going to be a positive number. So that will push up the partial sum a bit up to here. But then the next one is going to be taking a negative step again when m is equal to 3. So -1 cubed times a3, so it's minus a3. So you step down again. But then the next term is positive, you step up a bit, and then you step down a bit. up a bit, down a bit. So we observe this behavior that half or every second term in the partial sums, that splits the sequence of partial sums into two different sequences. One half of them, the ones that are after every negative step, they are going to be an increasing sequence. Remember the step size am, which is the absolute value of the step size, it is decreasing. So when you take this positive step up to here, your next step is going to be smaller. So you're not going to go down to this same level, you're going to go down to slightly above it. Okay? Because the step size you take from here to here is smaller than the step size you took from there to there. So all the ones that occur after a negative step, those are increasing. And all the ones that occur after a positive step are decreasing. Okay. So the sequence SK partial sums can be split into two subsequences. And these two subsequences are S2K minus 1. That's for every k equals 1 to infinity. So that goes through all the odd. So that's S1 there. This is S3, S5, S7, and so on. All the odd partial sums are the ones that occur after a negative step. S2K equals 1 to infinity. These are all the ones that occur after a positive step. So this is S2, S4, S6, S8, and so on. So the sequence of partial sums can be split into two subsequences. The subsequence of another sequence is just a sequence selected from some of the elements of the original one. Let's call this first sequence A and this second sequence B, just so I don't have to keep on writing them out. Where A is an increasing sequence and B decreasing. That's true because the AM plus 1 is always strictly less than AM, or less than or equal to AM, is what we need. And A and B will be converging towards each other since the limit of the step, the AM, which is the absolute value of the step size, the absolute value of the step size, we've said, is converging to 0. Okay? So that's why I was choosing to draw these even S's and odd S's converging towards each other, getting closer and closer to each other. Okay? Because we've said that this AM, which is the absolute value of the step size, AM is the term you either add on or subtract to get to the next partial sum. It's the amount you're stepping up or down by. If that's converging to 0, then those two sequences have to be converging towards each other. Okay. And then this is what ensures that the compound sequence, when you interleave these two sequences together to get the original sequence of partial sums, this is what ensures that the compound sequence, which is just the original sequence of partial sums, the compound sequence SK, all the partial sums, converges. And hence, the sum of our series converges. Remember, that's the definition of a series converging, is when the sequence of partial sums converges as well. So for instance, this alternating series test will tell us, this implies that, for instance, the alternating harmonic series this series here. Now, the harmonic series was when we just had 1 in the numerator, adding up all the fractions 1 over n. But if we now put an alternating sign on them, now this will be a convergent series. Now, actually deciding what the values of the sums are is a whole other matter. Okay. Other methods, and you'll see some of this in some of these alternating series we'll encounter in the second year maths methods course. But it's a whole other thing. Other methods are required to actually definitely describe the sums. Definitely describe the values of these convergent series. Okay, you can approximate the sums of them by just getting the computer to calculate some large partial sum of it that will be close to the limit. But actually getting some analytical, some precise description of the limit in general is hard. So that was theorem 2.8. Any questions about it, or anything I could clarify about it? So alternating series are generally easy to spot, because if you're looking at a formula for a series, in order to be alternating, there really has to be this factor of -1 to some power that involves the index and the series. It's generally easy to spot whether the series is an alternating one. So then, to decide on the convergence, the only way it can converge is if the absolute value of the step size that you're looking at is decreasing and furthermore converging to 0. It generally is quite straightforward to apply. Now we're skipping some of the formal details here, but thinking about the two halves of the sequence of partial sums, the fact that they must be decreasing and increasing, and the distance between them converging to 0, and the whole thing is bounded because the step sizes are converging to 0 as well. This is what makes the overall sequence of partial sums converge. Okay. So let's look at the root test as well. Theorem 2.10. Now the root test, what does... So this is a test we might use. We might use on a given series AM if the sequence of terms, where you take AM to the power 1 over m, taking the nth root of the nth term. So taking these increasing order roots of each term in the sequence. If this sequence of terms is easy to analyze, now how might that happen? How might it happen? And I'll show you an example in a minute where taking the nth root of AM is easy to analyze, because normally that, if you think of taking the 100th root of something, an algebraic expression, normally it's kind of awkward to deal with. The only real reason this might be easy is if the operations that are involved in defining AM, if the last operation is raising to the power n. In that case, taking the nth root will undo that last operation and maybe simplify the sequence term. Okay. So this usually only happens when raising to the power m is involved in defining the series term AM. So again, it's normally kind of easy to spot in a question setting. But what does this test say? This test says that you look at the limit as m goes to infinity of the nth root of AM. In a way, you're kind of comparing this series to itself, kind of in a way. If you can get this limit out to be a limit L, then, and again, the conclusion now is similar to the conclusions that happen with the ratio test. Then if L is strictly less than 1, then the series is convergent. But if L is strictly greater than 1, then the series is divergent. Again, the case L equals 1 is a borderline case where we don't get a conclusion. The test is inconclusive if this limit L is equal to 1. Now, the explanation for this is again based on a comparison with the geometric series. Because if you can establish this limit L, that means in the long run, the terms of our series are acting like L raised to the power n. Okay? If this limit L exists, eventually the term AM will be very, very well approximated by L to the power n. But now the series, the sum of L to the power n, that's a geometric series. Each term is this fixed multiple L of the previous term. And we know this geometric series, which our series is very, very close to, that will be convergent if L is strictly less than 1, and divergent if L is greater than or equal to 1. Because that value L equals 1 is the exact borderline between convergent and divergent behavior, we can't actually draw a conclusion of that. Okay. Now let's see an application. Let's see an application of the use of this. So there's one there in where is it gone? In the notes. Yeah, question 8, part C. 8C on page 20. It gives an example of the application of this test. So here we're examining, the question is to examine this series, which is the sum of all n from 1 to infinity, 2 to the n minus 1, 3 plus 4n, and that's all raised to the power n. Okay, so you can see now the role of this operation of raising to the power n. This is the terms of this series are like a compound term of order 1 polynomials in n, and then the final operation that's performed is raising to the power n. So this is a case where if we take the nth root of the nth term. Taking the nth root of the power n undoes that last operation, and it vastly simplifies the sequence term. Okay. So this looks ideal for the ratio test, for the root test, sorry. It's ideal for the root test because taking the nth root of that will simplify it. Okay. Normally, taking the nth root of an algebraic expression will be extremely hard. Will be hard to handle, but in this case, it's easy. So if we look at the limit as n goes to infinity of our sequence term, which is this, and then further we raise it to the power 1 over n. Well, these two operations are inverses of each other. You raise something to the power n, take its nth root, you undo that. So this is equal to whatever it is, the limit as n goes to infinity of 2n minus 1 of 3 plus 4n. Okay, this is a lot easier to deal with than the original sequence term. And indeed, there's nothing stopping us taking the limit here. Again, looking at a limit of the sequence of terms, if the terms are rational functions, these ratios of polynomials, the approach we should take is to divide above and below by whatever the maximum power of n we see, because that should reduce the whole thing to constants and terms that converge to 0. 3 over n plus 4. Okay, so I've divided above and below by n. I haven't changed anything. Well, I've changed the way it's presented. I haven't changed the value of the whole thing. And it's easy to see now that we can use our algebra of limits theorem to say this is the limit at the top divided by the limit at the bottom. And what's the limit of this linear combination? Well, it's linear combination of a constant and something converging to 0. The same thing down here, 4 and 3 over n. So those limits are going to be 2 on the top and 4 on the bottom. So the whole thing comes out to be a half. So then, from there to there and there to there, we were using the algebra of limits theorem. The algebra of limits theorem for sequences. So we have got a limit out, which is nice. So the idea is our series, originally up there, in the long run, if you wait around long enough, our series will be acting very much like the exact geometric series, which is the sum of all the powers of a half. Okay? And that is something, that was in fact the first ever series we looked at, adding up the powers of a half plus a quarter plus an eighth plus a 16th and so on. We found that converged to 1. And if you wait around long enough, the series we're looking at acts like that, or is the terms of our series are very closely approximating the terms of this convergence series. So that will make our series converge as well. Okay. So this is the L. This is the L that's mentioned in the series. And since this limit is less than 1, since this limit is strictly less than 1, we have a convergent series. Okay, now working out or trying to describe exactly what the sum of the infinite series isn't straightforward. Again, you can approximate it very well by just working out a large partial sum. Get the computer to add up the first 1,000 terms or whatever. But going beyond that, getting an analytic, formal description of the limit is maybe not so easy. Is that okay? Any questions or queries about that? Okay, so in this chapter, now I've still got 10 minutes left, so I'm going to do a few more examples, a few more exercises. But in this chapter now, we've just kind of got a couple of topics just left to do. There's a section on power series there in section 2.4, so I'll talk about that tomorrow evening in the lecture that we have tomorrow evening. And also there's a few other questions on that tutorial sheet which I've given out to you about using partial fractions to analyze infinite series. So I'm going to show you a few examples of that as well in tomorrow's session as well. But for now, I'd maybe like to just look at some more of these questions in the end of the chapter, and you know, have a look at some of the solutions of these. Maybe let's look at a few other parts of question 8. So please, if you got as we're going through these, if you have any questions or queries, please feel free to interrupt and stop me and ask me. So let's have a look at question 8b. So here we're looking at the behavior of the sum of n factorial over over n to the power n. Now there's no specific direction in the question about which test to use. So this is kind of the harder type of question we can meet on this question, on this topic. So we've got a whole suite of convergence tests there in the notes and that we've been looking at. Potentially any of them might be applied to this. The trick is to choose one that is suited to the series and one which will give us a definite outcome if that is possible. Do we have any feelings about or intuition about this series, about whether it is going to be divergent or convergent? So on the top, remember, a series converges if, and a series of positive terms, so these terms are all positive, there's just a lot of multiplication and dividing going on, and so everything's positive. These series converge if the terms can shrink and converge to 0 fast enough, then the series will converge. If they don't converge to 0 fast enough, then it will be a divergent series. Now, n factorial divided by n to the power n, general. See, on the top you've got a product of n things, n times n minus 1 times n minus 2, etc. On the bottom you've also got a product of n things, but it's n each time. So actually most of the terms in this product will be something, there'll be something smaller than n upstairs matched with n downstairs. So most of the time we'll be hitting it, multiplying it by things less than 1. So maybe it has a chance of converging if we can apply a suitable test. Okay. But now also we spot the presence of factorials and powers, and that also suggests using the ratio test. Okay. If we divide one term by the one that came before it, it'll be a closely related factorial, it'll be a closely related power. We may well spot simplification that we can do there. Okay, so let's try and use the ratio test. Okay, so if this is the sum of Bn, say, we'll look at the limit as n goes to infinity of Bn plus 1 over Bn. So this will be the limit as n goes to infinity of n plus 1 factorial over n plus 1 to the power n plus 1. And then we'll be dividing it by bn. So dividing it by bn is multiplying it by n to the power n over n factorial. And the first thing we might do is to deal with the factorials. That's the easiest thing. Remember, you've got factorial of n plus 1 divided by n factorial. Okay, so those two factorials are practically the same, except the one on top has an extra factor of n plus 1 in it. So everything cancels with each other to just leave this factor of n plus 1 on the top. And then we've got n to the power n over n plus 1 to the power n plus 1. Of course, then there's a factor of n plus 1 above and below, so that can cancel. And that reduces it nicely to n to the power n over n plus 1 to the power n. And you've got the same power on the top and bottom, so we can just write it as the fraction of those terms raised to the power n. Or another way of writing it is, it's the limit as n goes to infinity of n plus 1 over n raised to the power minus n. And the reason I flip it like this is when I flip it like this, we can split up the fraction as 1 plus 1 over n to the power minus n. But now this is a well-known sequence. A known sequence. We know that the limit as n goes to infinity of 1 plus 1 over n to the power n, we know that that is equal to this number e, which is the root of the natural logarithm. Okay. Now that is all kind of bound up in the definition of the logarithm and the definition of e itself. We'll just kind of make use of that as a fact for now. So this will imply that the limit as n goes to infinity of bn plus 1 over bn, well, we're taking 1 over that, you see, because we're raising to the power minus n. So we're looking at the reciprocal of these things. This will converge, sorry, this limit will be equal to 1 over e to the minus 1. Now we know approximately what the value of e is. E is 2 point something something. 2.178 or 718 or something. Anyway, it's two and a bit. That's the point about it. It's 2 and a bit, so E inverse is certainly strictly less than 1. 1 over E is strictly less than 1. So we do have a limit for the ratio in terms of this sequence, and we know that it's strictly less than 1. So by the ratio test, our series, which is the sum of, what was it, n factorial over n to the power n, is convergent. And that does seem to match with our intuitions that we tried to develop about it at the start. We did recognize that our sequence term involved multiplying together a load of numbers which were less than 1. The numerators, most of the numerators are smaller than the denominators. So those are numbers less than 1. And as the index increases, you've got an increasing amount of these numbers less than 1 multiplied. multiplied by each other. So that's going to be something that's getting smaller, smaller, and smaller. So that was our intuition at the start, and the presence of the factorials and powers led us to find the ratio test. We did get this curious limit coming out, but by making use of the known value of that, we were able to identify that we did have a convergence sequence and it was strictly less than 1. And so then we can reach our conclusion about that series. Okay, so that about ends it for this morning. So I'll see you tomorrow afternoon. We'll deal with power series and that thing about using partial fractions to analyze series, which are some of the questions on your tutorial sheet. We'll see you next time. Oh, also, I wanted to make the announcement at the beginning.